This is going to be a very different talk from the preceding talks because I'm not a historian. And I'm going to be talking about thermodynamic equilibrium. I figure someone should talk about thermodynamic equilibrium. But listening to these wonderful historical talks sort of makes me wish almost that I prepared a different talk where I talked more about the history of this. And so I wanted to preface this with a few words about where did thermodynamics come from in the first place? Because it's very much a continuation of the story that Michael was talking about. So he was talking about, there's this conviction that goes back to the early modern period that something is conserved, right? And it was partly empirical and partly a metaphysical convention, conviction that something has to be conserved. Well, what is conserved? Well, vis viva is not conserved. If vis viva is proportional to the square of velocity, I do that. It started out with a certain velocity went to zero, increased again, but as it was losing vis viva, it was going up, and if I want to move it from lower to higher, I have to do work, and eventually people realized that you can measure work and vis viva in the same units, and the amount of if you're ignoring friction, the amount of vis viva is lost is the amount of work it takes to go from this configuration to another. And we had the concept of work in the very first talk from the principle of the lever. If I want to raise 4 pounds 1 foot, the obvious thing to do is to just lift it. I'm exerting a force of 4 pounds over a distance of 1 foot. But if I'm more clever and if I have a lever, I can exert a force of 1 pound over a distance of 4 feet and achieve the same amount. And both of those involve the same amount of work. Now, problem is vis viva plus potential energy is not conserved either. I can do work on something and not not move it and not give it any velocity. Right? I'm exerting a force over a distance. I'm doing work. What's happening is the thing is heating up, and with the experiments of Joule, people Joule was taken to have established that there's a mechanical equivalent of heat, that you can measure heat. The amount of heat that you produce is actually proportional to, through friction, is actually proportional to the amount of work that you do. And so if you include vis viva kinetic energy, potential energy, plus heat energy, then finally you get something like we, so in the early 19th century, we get something like our modern idea of conservation of energy. And that's basically where thermodynamics starts, the idea that you can interconvert work and energy. Okay. Now, what I want to talk about, though, is concept of equilibrium and the process of equilibration. Because thermodynamics also starts from the idea that a system that is confined to a finite volume, given if it's isolated, it eventually, if you leave it alone long enough, it relaxes to some equilibrium state. And that equilibrium state is uniquely a function of its energy and any other conserved quantities that it might have. And there's something interesting that happens in the 19th century to this concept of equilibrium. Because people started having the idea, hey, wait, there's a mechanical equivalent of heat. Wouldn't it be really cool if that heat quantity was actually realized as kinetic and potential energy in the system, as mechanical quantities? And thus was born what we now call the kinetic theory of heat. So the idea is, okay, when I'm rubbing something, I'm doing work on it, I did not make the desk move as far as I could tell, but maybe I made made up the desk move faster. So there's kinetic energy associated with the desk that I can't see. Now, what's interesting about that is it means that the state of equilibrium that things tend to relax to is not actually a state in which nothing is happening. It's a state in which a lot of things are happening, in which there's a lot of motion going on, but it's happening at a microscopic level that we can't see. And there's a sense in which the entire statistical mechanics, science of statistical mechanics, is a consequence of this of the idea of equilibrium, not as a state in which everything is actually quiescent, but as a state in which there's a lot of activity going on, but it's going on at the microscopic level. So, what I want to talk about is not the history for the most part, but current discussions about how to explain this process of equilibration, given that we think that in light of the kinetic theory of heat, of the idea that you can actually apply ordinary mechanics to heat, because heat is actually something that is realized in mechanical properties of something. And that raises some conceptual puzzles. Okay, so I want to talk about how to explain equilibration. By equilibration, I mean the tendency of isolated physical systems combined to a finite volume to reach or approach a state in which observable quantities of either stationary values or a stable pattern of fluctuations. And the reason I say that is that not all systems actually equilibrate if I want to simply say observable quantities reach stationary values. A good example of that is Brownian motion. Yeah. You need a microscope to see it, but if you look at, say, pollen grains suspended in air or in a liquid, or ordinary milk, because milk is in fact a suspension. You've got blobs of fat suspended in water. If you look through a microscope, you'll see things jiggling around. And when this was first observed, it's called Brownian motion. Probably Brown wasn't the first to observe it, but it got named after him. People thought, okay, maybe we're seeing little microorganisms in the swimming, right? Or maybe what we're doing is we're observing, when we set up the system, we created some kind of eddies in the fluid, and if we leave it alone, it'll die down. But by the late 19th century, people had convinced themselves, largely through the work of a French physicist named Gui, that these motions just ain't going to go away. And it's not because, and you can't kill it. Like you can heat the thing up and hot enough to kill any microorganisms, and then these motions and cool it down again. These motions are still there. You can let it sit for a long time, and if they don't go away, so they're there. It doesn't settle. The system does not settle down into a state in which all observable quantities are stationary. And you could say, okay, the thing tends to, you could say the thing fails to equilibrate, or you can say, well, look, if you disturb it, you might set up some eddies in the fluid, but those will die down, and it does settle down into a state in which these suspended particles have a steady pattern of fluctuations of velocity, right? And the terminological choice. Do we call that equilibrium or not? In some of the philosophical literature, it's presented as if there's two rival concepts of equilibrium. But it is only a terminological matter. You can either say these systems like that fail to equilibrate, or we can say, okay, equilibration can include a stable pattern that things to settle into. Okay. Also, something that I think doesn't get enough emphasis in the philosophical literature is that, okay, I might think that this water, I disturbed it, it's sloshing around. I might think that the water is going to settle down into a state in which there's no sloshing and it's in constant temperature and it's um, in thermal equilibrium with the air, same temperature. But that actually, from the point of view of fundamental physics, is not a stable equilibrium state. The molecules have a certain kind of kinetic energy. Every once in a while, they could collide together to create a nuclear reaction. So if a system in which the number of hydrogen nuclei and number of oxygen nuclei is constant, each actually is non-equilibrium state. Okay. Well, you should wait so long. You should wait long enough, right? You let the thing sit for thousands and thousands of years, and it's still going to be water, right? But that's not an actual equilibrium state. That's not actually the state of highest entropy. It's a metastable state. And as a matter of fact, all the things that people call equilibrium states that we actually study in the lab are in fact metastable states, things that are approximately stable over very, very long time periods. And I think that's important because I actually think that if you're going to explain equilibration, what you're going to have to explain not just the tendency of things to settle down towards an equilibrium state, but you're going to have to explain differences in time scales. So the time scale of washing out of the ripples is a few minutes. Right? There's no longer any observable oscillation of the surface of the liquid. I'm pretty sure it's time scale of thermal equilibrium with the air around it is probably a couple hours, right? Time scale of everything turning to iron, I don't know. Huge. And actually, the equilibrium state of everything actually is everything turns into black holes and then they all radiate and there's there's nothing but Hawking radiation. Right? Okay. Everything else is a metastable state. Right? So if you're going to explain equilibration, you're going to have to talk about differences in time scales of different processes. Okay. Okay. And that's part of why there are clean mathematical results involve infinite long-term averages. And those are good, but what they tell us, if I tell you about the infinite long-term average of any system, tells you absolutely nothing about what you should expect in the next hour, the next day, the next 1,000 years, the next millennium. Okay. 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 Now, one interesting thing about the kinetic theory of heat is the laws of mechanics now apply to this process of equilibration. And we take that for granted, but that was actually a serious, a very serious conceptual shift. And some people resisted it until until the first decade of the 20th century. And not idiots. People like Poincaré was very skeptical of the kinetic theory of heat until 1912. Yeah, and what it means is that you're not going to actually be able to prove that you have a tendency to equilibrate for arbitrary initial states of an isolated system. And the reason for that is that if I can take, and people were saying this by, say, 1868, is I can take a mechanical state of a system that's headed towards equilibrium, reverse all the velocities, and it's going to be heading away from equilibrium. And the conclusion that the 19th century researchers accepted the kinetic theory, accepted as a consequence, was there's no way we're going to get equilibration results from dynamics alone. And basically what they concluded is the best we're not going to be able to prove that it's necessary, mechanically necessary as a consequence of the laws of mechanics of a system, that a system equilibrate. At best, it's only probable. Now, interestingly enough, this is also the 19th century, and this is a time when probabilities are starting to become more important in science, starting with the social sciences. So if I were doing a more historical talk, I would talk about that because, as I said, there's something interesting about the very idea that even though this water looks completely still, there's a lot of motion going on. Well, why can't I see it? Well, it's because there's, if the molecules are moving around, why is the surface smooth and flat? And the answer has to do with laws of large numbers. That a large number of individually unpredictable things can average out to something predictable. And this is an idea that Maxwell explicitly got from the social sciences. Because what was happening in the 18th century and the 19th century is the statisticians were getting all kinds of data about populations, and they were noticing things like numbers of murder per capita in a given city tended to be stable year after year. Right? So we can't predict who's going to murder someone or when. Would be nice if we could. But we can predict fairly reasonably how many murders per capita are going to happen in the course of a given year in Paris, for example. And people started talking about laws of large numbers, and the mathematicians started proving theorems about them, and those were explicitly imported from the social sciences into physics. Maxwell is completely explicit about that. Okay, so people are saying, okay, what we won't be able to do is derive equilibration results from the dynamics alone. We're not going to actually derive the conclusion that we're going to get equilibration for all possible initial states. We're gonna have to derive something like it's probably going to do this. Okay. And so here's Maxwell in 1870 saying the second law of dynamics has the same degree of truth as a statement that if you throw a tumbler full of water in the sea, you cannot get the same tumbler full of water out again. Right? Well, it's true. Right? If I throw this into the sea, maybe I'll do that tomorrow. Is it impossible that if I just scoop it up and just get exactly the same water out? Well, you know what? It could happen. Right? It's so bloody unlikely that I would disregard that possibility, but you can't say it's impossible. Right. Okay. And here's Gibbs. He's talking about mixing of gases, and he says the uncompensated decrease of entropy seems to be reduced to improbability. That's a reference to Clausius's form of the second law of dynamics, that there's no process that will move heat from a cooler body to a warmer body without some kind of compensation going on elsewhere. And late to the party was Boltzmann on this nearly 10 years after the British physicists were saying this. Boltzmann, by 1877, in response to Loschmidt pointing out what I said about reversibility, that if you change if you reverse the direction of all the velocities, then you'll get a process that macroscopically goes in the opposite direction. And he says, well, this shows how this is important. Where it shows intimately the second law of thermodynamics is connected to probability calculus. In all cases where the change of entropy can be negative, there are still are particular extremely improbable conditions for which it's positive. Okay, that's minus the change of entropy. Sorry. Yeah. So anyways, all quantities where dq over t can be integral of dq over t can be negative, they're still particularly extremely improbable in the initial conditions for which it's positive, and the proof that it will be almost always negative can be carried out only through probability calculus. And the reason I had those quotes from those other guys up there is that in a lot of the philosophical literature on statistical mechanics, it makes it sound like Goldschmidt was the first person to point this out, and actually Boltzmann, realized it a lot later than everybody else. Yeah. Okay. Okay. I think they're right. I think that probabilities are something that, if you're trying to do a correlation result, probabilities or something like that will have to enter into considerations. And if there are cases which we can make confident predictions, those are be cases which probability distributions are sharply peaked because of laws of large numbers or some other reason like that. Okay. Okay. So how do we want to explain equilibration? Well, in the philosophical literature, there's two broad families of approaches, both of which derive from Boltzmann, because everything in system mechanics derives from Boltzmann. I'm going to talk about those because I think that the one that is less popular in the literature is actually more on the right track. So let's just take a particular example. Suppose you walk into a room and there's a container divided into equal volumes by a partition with a small hole in it. And equal volumes is not important. They just use that to simplify things. Okay. And at the time you run across it, there's air in it, but the pressure is higher in the left half than the right. Okay, what's going to happen? Not a rhetorical question. I'm serious. It's not a rhetorical question. What's going to happen? The pressure equalizes. Okay. Pressure equalizes, right? And then once it's equalized, what happens? It stays the same. Is it really? Am I always going to have exactly the same number of molecules on either side? Approximately the same if it's I didn't say how many molecules there were, right? I didn't say it's a macroscopic liquid gas. If it's a large number of molecules, then there's going to be approximately a constant number of molecules on each side. But if it's small, then if there's only one, obviously, then there's going to be one molecule that spends half the time on one side and half the time on the other side. Okay. Okay, good. Okay. Now, now I want to be able to model this as a physical problem. Right? How's it going to happen? So suppose, and we're going to talk later about the reasons you might have to suppose this. Suppose that you think that the evolution of certain features of the gas, crucially the amount of gas in each subvolume, can be adequately modeled by the following model. Each molecule has independently a certain probability per unit time, lambda, of making a transition from one solid bottom to the other. Okay. And the reason that I say suppose that certain features of the gas can be modeled this way is I'm basically treating the molecules as if they're classical things that can be ascribed definite trajectories. And of course, they're not. However, it might be that if I did this entirely quantum mechanically, that the probability, quantum mechanics is going to be a probability for amount of mass in each side. Under certain circumstances, particularly if this is a dilute gas, that quantum probability distribution is going to evolve in the same way that a classical probability distribution will. Okay, so call that the transition probabilities postulate. Okay. Now, if I assume the transition probabilities postulate, the reason I chose this example is you can actually solve it's a nice simple problem. You can solve it exactly. It's a variant on a problem introduced by the Ehrenfests. It's sometimes called the dog-flea model. They were imagining fleas jumping from one dog to another. Oh. Okay. Actually, I don't know if they were imagining it, but I think they phrased it in terms of urns, and then somebody at some point started talking about it in terms of dogs and fleas. Anyway, Okay, so at any given time, there's been a number of molecules on the left side. So suppose at some time, the time you come in, time t0, there's n0 molecules on the left and m0 molecules on the right. And that plus the probability postulate gives us a probability distribution over the future values of n of t. And if you work it out, the expectation value of the number of molecules on the left side exponentially decays towards n over 2. Right? And the statistical spread of the distribution, initially 0, because I gave as a condition of the problem, there's n0 on one side and m0 on the other. It gradually widens and it approaches square root of n over 2. Okay, and if you graph it, and it looks like this, where the colors are supposed to indicate the statistical spread. Things look weird in the graph when you're too close to the thing because my maple, which I was using, couldn't handle something very sharply peaked. But yeah, so it's very sharply peaked probability distribution at the left side, gradually decays towards a stable probability distribution. Never reaches it. Okay. Okay, so a probability distribution converges towards a stable distribution in which there's no net tendency for change in the number of molecules on the left side. There's a stable probability of fluctuations away from the mean. The statistical spread of fraction of molecules that are on the left side is proportional 1 over square root of n. So if it's a macroscopic gas, something like 10 to the 24 molecules, that's square root of that is 10 to the 1 over 10 to the 12. You're not going to observe it. If it's a microscopic system, and people who are working in quantum thermodynamics actually do apply thermodynamics to microscopic systems, that might be not negligible. Okay. So if the number of observable fluctuations are so rare as to be negligible, but we don't need to assume that. The analysis goes through for small samples of gas. And I've already said, in the cases where fluctuations aren't negligible, we have two options. And this is only terminological. We can insist that equilibrium must mean a situation in which all observable quantities have stable values and say that the system fails to equilibrate. Or we can accept that there are fluctuations in equilibrium and speak of an equilibrium distribution of fluctuations. And in the physics literature, option B is pretty much the universal choice. And in the philosophy literature, option A is almost the universal choice. Okay. If we accept option B, then it makes sense to distinguish between an equilibrium distribution, which is a stable probability distribution for observable quantities that systems approach, and a special case, which is an equilibrium state in which the equilibrium distributions of the observable quantities, the macro variables, are sharply peaked, and we can speak of equilibrium values of those macro variables. Okay. Only a terminological choice. And the reason I'm emphasizing this, the philosophers in the audience will know, is in the philosophical literature, there's allegedly a debate between two rival approaches to statistical mechanics, and one of the arguments that they're incompatible approaches is they have different conceptions of equilibrium. It's only a terminological choice. Okay. Okay. So suppose you happen to find a container divided into equal parts by prediction with a small hole in it. Same setup as before. Contains air, and at the time you happen upon it, the pressure is higher in the left half and then in the right. And it's been, you don't know, it's been sitting there for a while. You don't know how long it's been. But suppose it's been sitting there for a non-negligible amount of time. What should you expect about the past of it? Like a minute ago. Not a rhetorical question. What's that? Yeah, it's been equilibrating. Right? Yeah, in fact, you should expect that a minute ago there was even a greater inequality of pressures between the sides. Right? Yeah. Okay. Okay. And basically, you know, given that probability postulate, that turns the questions about the past into a question about statistical hypothesis testing. Because you've got, let's take, t minus 1 is 1 minute ago. For each n from 0 to number of molecules in the thing, there's a hypothesis says at t minus 1 there were n molecules on the left side. Our evidence is the number of molecules on the left side at t0. And basically, within statistical hypothesis testing, there's two families of methods. The standard ones basically compute. I'm sorry. There's standard hypothesis testing and Bayesian testing. The difference is that the Bayesians will seek to give you a posterior probability for things, and standard probability, so hypothesis testing does not. But in either case, the likelihoods play a key role. And the confusing bit of terminology, likelihoods associated with hypothesis is not the probability of the hypothesis, but the probability of the evidence conditional on that hypothesis. And so if you open up a standard statistical hypothesis, statistics textbook, you can say, okay, one good thing to do is to adopt as your estimate to the quantity, you're trying to estimate the maximum likelihood estimate, the one that makes the evidence the most probable. Choose the value of n that makes what you saw most probable. Bayesian hypothesis testing says, okay, you're going to start with some prior probabilities about these hypotheses, and you're going to update your probabilities by conditionalizing the evidence. And again, the likelihoods play a big role. And doing that boosts probability of hypotheses and make evidence more probable. So on the standard hypothesis testing, you just pick as your estimate the value of n that makes the evidence most probable. On Bayesian, you start with certain priors. We'll talk a bit more about what those priors should be. But the hypotheses that make the evidence more probable are going to be boosted by conditioning on the evidence. Everyone got that? Okay. Okay. Now, Bayesian inferences requires priors. And there's a number of different approaches to that. There's an approach called objective Bayesian that attempts to prescribe unique rational degrees of belief. Credence is philosophers' jargon for degrees of belief modeled numerically. Objective Bayesianism attempts to prescribe unique rational credences for every evidential situation. In my opinion, it doesn't succeed. Attempts to do this usually invokes something called a principle of indifference. And the principle of indifference is either empty or inconsistent, because it either says, pick a partition of things that you judge to be equally probable and judge them equally probable, or it leaves it so vague that you can actually have inconsistent probability assignments. In the philosophy of probability, there's something close to a consensus that the principle of indifference doesn't make sense, though there's 2 or 3 people still trying to defend it. Right? Another one would be radical subjectivism that says the only constraint on credence is that they obeys to the law of probability. Very permissive and permits dogmatic priors that preclude learning from experience. So I could just pick my favorite hypothesis and stick to it no matter what. If I assign probability 0 to all other hypotheses, then conditioning on the evidence is not going to change that. And there's also something that my teacher, Agnes Shimoni, calls tempered personalism. It does not attempt to prescribe unique rational credences for every evidential situation, but it also doesn't go as far as radical skepticism. Basically, he imposes what he calls a tempering condition is, okay, don't be dogmatic. Like any seriously proposed hypothesis, you can be suspicious of it, you can be skeptical of it, But if someone proposes a theory and you might be skeptical, but if they actually give you really good evidence for the theory, your probability, your prior credence should be so low that it remains low. Okay. Okay, so as I said, the likelihood, and so here are the likelihoods. Unsurprisingly, they basically the maximum likelihood basically continues that line of that we had on the other graph. And so the maximum likelihood is just what Miguel said. It's it was equilibrating. It tells you that it was equilibrating a minute ago. Right? Pretty much the same as when you go towards the future. So as long as your priors aren't too dogmatic, then you're going to favor something close to the maximum likelihood line. And if you're doing standard hypothesis testing, then you're just going to pick the maximum likelihood estimate as your estimate, and you conclude. The conclusion is you're pretty sure, you're not absolutely certain because this is probabilistic, but you're pretty sure that the pressure was hot, the difference was higher a minute ago. Okay. Now, people who are familiar with the literature on statistical mechanics are going to recognize why I'm doing this, and if you're not, then I'll explain later. Suppose an evil sorcerer, suspected by some to be the notorious prince of indifference in disguise, casts a spell that constrains you to adopt that equilibrium probability distribution, the one that gets approached if you leave the system long enough as your priors. Okay. That your credence about the state system at time 0 are obtained from the equilibrium distribution by conditionalizing on the proposition that what you saw at of what you saw at time 0. Right. Okay. And you say, you beg for mercy. You say, the thing hasn't been. Why should I use the equilibrium distribution? The thing hasn't been sitting there that long, right? But the sorcerer doesn't care. Okay. And in an Orwellian move, similar to War is Peace, the principle calls this a principle. The sorcerer calls this a principle of rationality. Okay. If you do that, and this is a mathematical thing, then your expectations toward the past mirror your expectations toward the future. And I think the way to think about this is if you start with the equilibrium distribution, it's just steady state. It doesn't, it doesn't make a distinction between the past direction and the future direction. So if you take the equilibrium distribution and you conditionalize on states of affairs at one time, you're going to get expectations towards the future and expectations towards the past that are symmetric. Right? So if you adopt this as your prior, you're going to regard it as most likely that what you saw was a peak, a momentary peak away from the equilibrium the equilibrium state. Basically, if you wait long enough, you're going to get all kinds of fluctuations. It's as if the thing, the thing had fluctuated randomly into this state. Okay. 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 So, okay, that's bad. All right. You get the wrong answer. So you say to the sorcerer, well, okay, can we compromise? For reasons I understand, you're constraining me to adopt this equilibrium distribution at some point and conditionalize on some macro state. But that leads to bad retrodictions. It leads to predictions that are okay, but bad retrodictions. Can we just push that back so far back in the past that I don't care about retrodictions before that? So you beg leave to push it back so far in time that you're uninterested in making retrodictions for prior times, and then you conditionalize on whatever macro state is well supported by the normal inferential procedures of science. That is the conclusion that we would have come to if we hadn't had the sorcerer intervene. Okay, the reason, now those of you who are familiar with the literature, philosophical literature on system mechanics will understand why, I guess, why I told this story. Because what I just described is actually the mainstream approach in the philosophical literature on explaining equilibration. It privileges equilibrium distributions, and to fix the problem that if you're conditional on the current macro state, you get, expectation is motion towards equilibrium, but also towards the past. So whatever, and if you apply this to everything you see, then you get the conclusion that okay, all of this is just a momentary fluctuation out of equilibrium, and everything that we think is a record of the past is actually an illusion. But okay, so there's a certain approach to explaining equilibrium just privileges the equilibrium distribution that says, okay, where you going to apply it is in the distant past. And what you do is you accept from the scientists who are studying cosmology, who haven't been bewitched, what conclusions do you, what conclusions do you come to about the early universe? And I'm going to take as my probability postulate as my probability postulate, I'm going to start with an equilibrium distribution and just conditionalize on those conclusions. Why would you do that? Part of the popularity of this approach comes from a book by David Albert, published like 25 years ago, and and some people get what he says wrong. So he calls this postulate that there is this this sort of macro state of the in the early universe, the past hypothesis. And some people get the impression that he's saying, well, you have to do this in order to science. You have to make this postulate. And what he actually says is, it'll be perfectly clear that all such posits are about to fail, meaning taking an equilibrium distribution and conditionalizing on a macro state, unless they concern less than the entire universe, at nothing later than its beginning. So it's if we're going to do that, if we're going to adopt the sorcerer's prescription, it has to be done at the beginning of the universe and applied to the whole universe. But there's no argument that you have to do that. So the question is, well, why should one ever make such a posit? And there's surprisingly little literature on answering that question. And it's not a standard move in the statistical mechanics textbooks of non-equilibrium system mechanics. Sometimes people who come into this from the philosophical literature will end up erroneously saying that this is a standard postulate of statistical mechanics, and yes, that's not true. What you'll find it in textbooks of equilibrium statistical mechanics, but they say at the very first pages we're dealing with systems that have sat long enough to equilibrate. And the textbooks of non-equilibrium statistical mechanics often say that the postulate of this form is recommended for what they call aged systems, systems that have been evolving still long enough to equilibrate. Okay. So why, people who are familiar with the literature on philosophy of system mechanics can testify what I've just described is the standard approach. Privileges equilibrium distributions, but just puts in by hand a past hypothesis. Why should anyone regard those distributions as privileged for systems that have not had time to equilibrate? Oops, I've got these in the wrong order. Well, sometimes people will invoke a principle of indifference, but as I said, that is kind of in disrepute in the philosophy of probability literature, and David Albert vehemently denies that he's doing anything like that. Okay. Sometimes people say, okay, well, these are temporally invariant. This is a stable distribution. Well, but yeah, why should I think a stable distribution is the right thing to do to adopt for a system that hasn't had time to equilibrate? And if you've got a system that has some kind of long-term behavior that it settles into, then the stable distribution is going to favor that. Okay. And David Albert's actual answer is it leads to the correct inferences towards the future. I mean, that's what he says. Avastin. And but if the strategy work, it can't single out that distribution uniquely, because if I impose it at a given time, I should be able to evolve it forward and get good predictions. But that also means that if I impose it at a later time and evolve it forward, I should be able to get good predictions. So if the strategy works, it cannot single out that distribution uniquely. Okay. In our example, any probability distribution over microstates that yields that transition probability postulate yields the right inferences towards the future. Okay. So this disastrous prediction problem, I just wanted to reiterate, because people get confused about this in the philosophical literature. It's not inherent to statistical mechanics, but it arises when one employs a uniform distribution to a system that's not had time to equilibrate. Okay, so by the way, how much time do I have? I should be wrapping up soon. Yeah? Okay, so I'll wrap up in the next 10 minutes. Okay. All right, so why should we do it? Well, as I said, pretty much everything in statistical mechanics traces back to Boltzmann. And when in one of his papers where he's trying to prove that the gases approach a certain equilibrium distribution of velocity is now called the Maxwell-Boltzmann distribution. He uses, at first implicitly and then later explicitly, something that the Ehrenfests, in a wonderful encyclopedia article that they wrote in 1911, so Paul and Tatya Ehrenfest, called the Stoffzahl-Ansatz, the collision number assumption. And those of us who work in this thing tend to just use the untranslated German. And that basically was the postulate that if you got molecules colliding that are about to collide, there's no correlation between the velocities. And it's explicitly a temporally asymmetric assumption, because it has to do with molecules that are about to collide. You can't assume that there's no correlation between molecules that are about to collide and molecules that have just collided, except in the equilibrium condition. So if something is heading towards equilibrium, then the Stoffzahl-Ansatz could apply to molecules quite about to collide, but molecules that have just collided are going to be correlated in their velocities. And the equivalent of that in, if I'm imagining, if I'm imagining that my probability distribution, even if it's a quantum probability distribution, evolves just the way a probability distribution over a bunch of things bouncing around randomly, then the intuitive idea is that molecules are heading towards the wall should neither favor nor avoid the hole. So if I just assume, anywhere in the gas near the wall, there's pretty much the same distribution of velocities, then the proportion of molecules, the number of molecules that in a given time they're headed towards the hole is just going to be proportional to the total number of molecules in the gas. And that gives you the transition probabilities postulate. Okay. And so, the intuitive idea is the molecules heading towards the wall should neither favor or avoid the hole. Probability that the molecule hits a given area of the wall is proportional to the area, whether or not the area contains the hole. And well, suppose it were false. Right? Suppose that molecules head towards the wall were more likely to be headed towards the hole than other parts. Probably ask, well, why? Do you think the hole is like drawing the molecules towards it or something like that? Okay. All right. How and notice, this is actually a temporally asymmetric assumption, because away from equilibrium, we do expect that if we look on the low pressure side and look near the hole, there's going to be more molecules moving away from that part of the wall than there would be in other parts. Okay. 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 So suppose that that's true. Suppose on the low pressure side, most of the molecules near the hole are on trajectories heading away. That, if reversed, would take them back to the hole. We ask why. Natural answer is that's where they came from. That those molecules were on the other side and they came from the hole. And my claim is that's a perfectly adequate explanation. It doesn't need to be supplemented by anything else. However, I just point out, the temporal inverse of this would not be an adequate explanation. Okay. If most of the molecules near the hole were on trajectories that head towards a hole, and someone asked why, and I gave the temporal reverse of this explanation, well, because that's where headed, that doesn't explain it. And why am I saying this? Because the question we started was, well, how do we explain equilibration? And equilibration is a process that is temporally asymmetric. We expect things that are away from equilibrium to head towards equilibrium, and things that are now not in equilibrium but isolated to have been further away, not closer to equilibrium in the recent past. Okay. The very notion of explanation, I claim, is temporally asymmetric. So there's nothing at all wrong with taking a temporally asymmetric premise like our, like the transition probability postulate as to explain a temporally asymmetric temporally asymmetric phenomenon. Right? So and this is a very unpopular move in the current philosophical literature. Some would say, well, look, no, what you ought to do is forget everything you know about temporal asymmetries in the world. Try to adopt a view from a God's eye view that does not distinguish, or assuming God is an atemporal being, right? A God's eye view that does not distinguish past and future, and hence reject any temporal asymmetry of explanation. Why? Why should we do that? And what people often say is, well, the fundamental laws of physics are invariant under time reversal. They're not temporally asymmetric. Okay, that's true. Even if you acknowledge that the weak force is not T invariant, is not a asymmetry of the relevant sort, where's the argument? And I think that if you try to fit out the argument, and it's rarely done in the philosophical literature, it'd be something like, explanations must be in terms of law and initial boundary conditions, because laws by themselves don't tell you anything at all about what things are going to be like. And all the explanation has to go into the laws. Boundary conditions must be taken as brute facts. And so the best we can do is impose temporally asymmetric boundary conditions like the past hypothesis with no explanation of why it should be. My claim is that this implicit, sometimes explicit premise accords very poorly with both scientific practice and everyday practice. Example I often give is, suppose that the next level of people looking at the cosmic microwave background, there was this pattern around the celestial equator of cooler spots that spelled out the Lewis Carroll's Jabberwocky. And you ask why. It says, oh, that's just how things happen to be at the beginning of the universe. No. You would ask for an explanation, and probably would involve, your first explanation is, okay, something went wrong with the measurement. Okay. So this premise 3 accords poorly with both everyday and scientific practice. Okay. So as a matter of fact, we tend to explain certain kinds of correlated or coordinated behavior in terms of past common causes. In practice, we tend to regard certain kinds of initial conditions as unlikely in the absence of a causal explanation. So, this business about the, something being written in the cosmic microwave background, I would know, okay, you want to know what caused that. You wouldn't just accept that as a brute fact. Right? And some people in the philosophical literature will say, okay, that's a mistake. You should try to cure yourself of that habit. My recommendation is don't try to convince yourself it's a mistake. There are causal relations to nature, and they are temporally asymmetric, and it's perfectly good explanation to practice to look for explanations of correlations in terms of past common causes, and not to apply the same thing towards the future. Okay. And for the philosophers, this is not a project of trying to get rid of all talk of, reduce all possible talk of causality or possibility and stuff like that to purely categorical things. If you don't understand that parenthetical remark, you're better off than those who do. Now, there's an issue with applying this kind of reasoning to our case because basically it means treating the velocity distribution in each subvolume as effectively random. And that means that I'm thinking of basically a process of equilibration going on that randomizes the velocities within each subvolume, which goes quickly compared to the slow leakage of gas from one subvolume to the other. Right? And it can't be strictly true because, on the low pressure side, we'll have molecules moving near the whole differentially moving away from it. But, the assumption is those aren't very important for the macro variable that I'm looking at, which is number of molecules inside. Because what's going to happen is that the ones that get away the hole, so they're going to bounce around and they hit lots of things. And by the time they head back towards the hole, the velocity is effectively randomized. Right. Okay. Okay. So the comparatively slow process of equalization of pressure in each chamber can be explained on the assumption that within each chamber, the velocity distribution is approximately isotropic. And this can be argued basically on the basis of Boltzmann-Rickmely argument, which assumes that the velocity of molecules about to collide are uncorrelated. Again, a temporally asymmetric assumption. Okay. And Boltzmann's rationale, sorry, there's a typo, was that, basically, if you got dilute gas, then, things are going to collide and then, head off, and that's effectively a new environment. Okay. So I claim that in a lot of studies of equilibration, implicitly or explicitly, there's something like this common cause postulate going on. And there's some assumption that motivated by something like a common cause principle to the effect that correlations to explain in terms of past common causes. You might try to formulate this as events whose past light cones don't overlap are uncorrelated, but that would be totally empty. Right? We typically require the common cause to be in the recent past. And the reason is that there are processes that tend to wash out the correlations. And those processes are precisely the sorts of processes of the sort that we're trying to explain. Right. So the common cause principle only has teeth if the something like the sort of equilibration process that we're trying to explain is in effect, and we're using the common cause principle to explain equilibration. Is that a problem? If you look in the literature, Carlo Rovelli, in particular, has argued that temporally oriented causation is rooted in the tendency of systems to react towards equilibrium. There's a paper in Philosophy of Physics with pretty much that title from a year or two ago, I think. And what I've argued that in at least some cases we can explain equilibration by reference to temporally asymmetric causal considerations. And okay, it might look okay. This is exactly the sort of things that philosophers like. There's there's two opposing views, which which is prior, which explains what? Do we ground the temporally oriented causation in the tendency of systems toward equilibrium, or is it vice versa? And I think if I gave this talk like 5 years ago, I would have argued, okay, this is the right way to think about it and not that, right? But I no longer think that. I think that it is true that equilibration can be explained by invoking something of the flavor of a temporally asymmetric common cause principle. It is true that temporally asymmetric causation is employed in these arguments requires a tendency to equilibrate to have any bite. So Carlo's right about that. Causal considerations configure explanations of equilibration. Equilibration is a condition of possibility for those causal considerations to hold. And we don't have to ask which is prior or which grounds which. I think that the tendency to the pull towards asking which grounds which, or which of these prior, is rooted in some kind of Aristotelian or scholastic view of philosophy that I actually think that we should reject. All right. And it's none.
Whether you could say more about why temporally asymmetric causal relations require assuming equilibration to have any bite, or what was this?
That's an argument that I didn't go into, and when I write this up, I'm going to go into it. That's something that is in a paper by Carlo Rovelli, and basically the idea is that in equilibrium, you don't have like any causally asymmetric relations between things. Like if typically the way we judge causation, if we mere correlation is not causation, right? And if I want to know, the example that's often given is there might be a correlation between a barometer and an incoming storm, and if I want to know which causes which, I can do an intervention. Does setting the barometer change the behavior of the weather? No, it doesn't. And so the claim is that circumstances in which you can do an intervention like that requires actually there to be something temporally asymmetric going on in the first place, and in a situation of equilibrium, you just have correlations, between things that are temporally symmetric. So, I'm not doing justice to the argument. I'm sorry, I'm still a bit jet lagged in this form, but yeah. If you want to know more details, look at the argument for Ravelli. It's in the Journal of Philosophy of Physics, like last year, something like that.
No. Okay, thanks, Ming. Can you just go back to the last example when there are few particles in the left, and you say, yeah, we can induce that there are more particles that coming from the hole or something like that? Yes, when we say, yeah, the fact that we can find more particles that jump out in the left part is because they come out from the hole. Because, yeah. Yes, the question is, if we try to rewrite this with the probability theory, it's a bit complicated to write the conditional probability about the fact that more particles came out from that or no?
So I'm assuming that whatever probability distribution you have over microstates, it satisfies this transition probabilities postulate. And if you just do that, then if you at a certain time you have if you assume that holds at every time, and at a certain time there are more on the left than the right, and you want to make inference about what was past, this by itself isn't going to give you any of that, because you need higher probabilities about past states. My claim is, if your prior probabilities of past state, and there are prior probabilities that give the wrong answer. If I take the sorcerer's probability distribution and basically say, so the sorcerer's probability distribution has each molecule has probably 1/2 on being either side, and so it's very sharp. For a large number of molecules, it's very sharply peaked around even probabilities. If you take that, then you get the disastrous retrodictions. My claim is that those violate the Schroeder tempering condition. That you're dogmatically assuming that you're attaching very high probability to the higher probability to the equilibrium state, so much that any conditioning on any evidence is just going to give you, okay, what's the minimal deviation from the probability from the equilibrium state that's compatible with the evidence. Right. So yeah. So my claim is, any reasonable probabilities will give you right. Those yeah. I calculated this for 100 molecules, and so we've got this white band, right? Which is the standard deviation of that probability distribution. If I did this for a macroscopic number of molecules, like 10 to the 24, I couldn't graph that band. It would be very sharply peaked around the maximum likelihood value. So the claim is, unless you have really dogmatic priors, which are peaked, very sharply peaked. Like so the sorcerer's priors are very sharply peaked on that line. And so much so that conditionalizing on there being 70% in the left-hand side at this time, it will just bring you back to that. My claim is that those violate the Shimoni tempering condition. They're excessively dogmatic. But anything else, anything that's not dogmatically peaked around some particular values, this is going to be too much. These likelihoods are going to be so sharply peaked around the maximum likelihood value that you're conditionalizing on the evidence is going to give you conclusion that the higher the behavior at time a minute ago was close to the maximum likelihood value.
Great, thanks, Wayne. This is fantastic. I have a question rather that I want to learn more about from you, which is in the beginning when you talk about the large number theorem, you said that if the degrees of freedom of the system is large, so you have like smaller perturbations, smaller fluctuations, so that's around the equilibrium state. But are you suggesting that if the size is small, so you could allow for large fluctuation? And in that case, what would the stable pattern of fluctuation be? And then what kind of thermodynamic?
Yeah, 100 isn't very big. Yeah. So let's see, where's that? Where was that other
It's
graph?
the very beginning, actually. No, I'm asking this because some people might say,
Yeah. Like so, yeah. So the stable probability distribution is centered around 1/2 with a spread like that. Yeah.
yeah. But what about like number just 2, 3, very, very small?
Yeah.
Consider
So
one.
if it's 1, then the stable probability distribution is 1/2 on each side with a standard deviation of 1. Yeah.
Okay.
Yeah.
So in that sense, you can still talk about equilibrium state.
Equilibrium distribution.
Okay. Yeah.
Yeah. So here's a terminology. Here is a terminological confusion. I think that state is used in system mechanics in 2 different senses. And there's a reason for it. The statistical and mechanical analog of a thermodynamic state is a probability distribution over microstates, because a thermodynamic state drastically take a gas. I tell you its total energy in the volume. That really drastically underdetermines the microstate, right? But a thermodynamic state basically is specified by just those parameters. So standard move is a the quantum mechanical, the statistical analog of a thermodynamic state is the probability distribution over mechanical microstates. And however, usually we also use the word state to mean a specification of the variables, right? And you might think state might mean a specification of macro variables. And so I think a good let's see, where did I have that slide? Yeah. What you'll see in some of the textbooks of non-equilibrium system mechanics is they distinguish between equilibrium distribution and an equilibrium state, where an equilibrium state is a special case where all we need to do is specify macro variables and say, oh, with almost certainty, those are going to be the values of macro variables. And I think this use of state in 2 senses is part of what fuels this idea that there are rival approaches to statistical mechanics, Gibbsian and Boltzmannian, because sometimes the word state is meant to be a specification of values of variables, and sometimes because the statistical mechanical analog of a thermodynamic state is a probability distribution over microstates, people use the word state for such a probability distribution. Again, it's just terminological.
This is clarifying, but just a small follow-up. If we only consider like the one particle situation, and so that you have like distribution 1/2 in each side, and with deviation equals to 1. Would you say that's a stable distribution?
Of course.
Okay, perfect.
Because it doesn't change with time. At any time, there's a probability 1/2 of it being on a given side. Yeah. Right. So if you started out on one side, then what you'll have is a decay towards that stable distribution. Right?